What is scheduling? Before we go into that, let us understand how the programs work. So as mentioned here, all programs will have two parts. One is a CPU burst and another is IO burst. So what does CPU burst mean? CPU burst means computation of results for a given data. Say for example, you have already captured some signal via ADC and now you want to compute to make sense of this ADC data. The next is IO data. That means waiting for some IO to happen. Now taking back our ADC example, now when a signal is fed to the ADC peripheral, you are waiting for the interrupt to come from the ADC peripheral, which indicates that it has completed the acquisition. Okay, so then while it is waiting for acquisition, the CPU is ideally free. So what does scheduling algorithm do is that it allows other programs to get the CPU while the current program is busy waiting for an IO. That means, let's say you are waiting for the signal to come from ADC peripheral that it has completed acquisition. Maybe you can run a program which is controlling some sort of, let's say, a relay via a GPIO. Okay. Now, to illustrate, let's say I have two processes or programs or tasks depending on context. Let's say P1 is scheduled and it is running on the CPU. Then at some stage it is waiting for IO to happen. Now in this time the CPU is free. So what happens is that the scheduler algorithm gives the CPU to P2. So similarly P2 will wait for its IO operation, and now scheduler finds that P1 has completed its IO operation and now it wants to process the data, whatever it has got through IO operations. And now P1 will start running, and again subsequently P1 will wait for next set of IO and P2 will be ready and P2 will schedule, and this continues so on. Okay. Now what happens is that if I want to give an illusion CPU ownership, so first it will be with P1 and subsequently go to P2, P1, P2, P1, and so on. And it happens so fast that you hardly notice the switch. This gives the illusion that both P1 and P2 are running at the same time on the same CPU core. But in reality, it is just sharing the CPU. I would like to give you a cooking analogy to remember this. Let's say you want to cook two items for your breakfast and you only have a single stove burner. You want to cook fried egg and a toast to go along with it. Now, if you cook fried egg completely first and then make toast, or the other way around, where you make toast first and then cook fried egg, this is called as non-preemptive scheduling. And if you time share and cook fried egg and toast together, this is called preemptive scheduling. Okay, that means you cook, let's say, fried egg for maybe 30 seconds and then immediately switch to cook toast and then switch back to cook fried egg until both of them are completely cooked. Okay, now which algorithm to choose depends on the application you are building. Let's say in the given cooking analogy, I feel non-preemptive scheduling works best. Okay, so it really depends on what application you are building. Okay, now what is non-preemptive or cooperative scheduling? Now, if a new task is scheduled, that means given CPU to run only if an existing task running on the CPU encounters below mentioned either of two conditions. Either it could be waiting for an IO operation and by itself gives up the CPU until that IO operation completes, or the task has completed and is terminated. Now, this brings to an important point, which is if this algorithm is selected, then it is the responsibility of the programmer to make sure that the task is giving up the CPU by calling appropriate system calls or OS provided calls. What these OS calls or system calls do is that it invokes the scheduler to schedule next set of programs which are ready to run. Okay. Now, if you are more interested, you can find a ton of literature on the web where you can do much more deeper study on this non-preemptive scheduling. Please feel free to browse and dig deep into these algorithms. I hope this brief introduction about non-preemptive scheduling is good enough for us to start implementing our non-preemptive scheduler. Now let's proceed to implement our non-preemptive scheduler on STM32. If you have any questions, please do drop them in the comment box below and please do like, share and subscribe to my channel. Thank you.